This is FE Peer Review. The date is May 29th, 2021. Comparing long-distance observations on flat and curved surfaces. This video came about in response to a question that Gary Waibenga left towards me, directed to me. We were both looking at a Conspiracy Cats video. Gary said, if the guy who took the Blackpool Tower picture moved couple miles further away back from Blackpool Tower and took a picture, would the tower then appear below the mountains? It's a good question that got me thinking, and I realized that I couldn't answer it on the spot other than by saying it depends, which is kind of annoying. So I told Gary I needed to take some time, do a little bit of analysis, and then I'd get back to him with a more carefully thought through answer, and that's what I'm doing. So what I've got here are some slides that I put together, and these are diagrammatic. They are not to scale. They represent an observer. We see the observer at the far left of the frame, little red circle, and in a smaller object and a larger object further away. And in one case we're looking at a flat ground plane, and the other a curved ground plane. So I wanted to avoid doing math in this video. I wanted to work from a purely graphical point of view, and I am considering light traveling in straight lines. That means from the observer's eye, or from the object to the observer's eye in a straight line, which means no atmospheric refraction, zero, straight lines. No curves due to some sort of perspective effects that I have yet to be seen demonstrated, but which some flat earthers have proposed. I'm ignoring curves. I'm ignoring light traveling in curved lines. I may cover the issue of atmospheric refraction in a separate video, but for the purposes of this video, I'm ignoring it, and I think that that's going to make my point more clear. So we have an observer who's at a certain height. We have an object of a certain height and a second object of a certain height. Same for flat or curved surfaces. Now, it's immediately apparent that if the height of the observer is very, very small compared to the other heights and compared to the horizontal distances, we can just as well consider it zero, and it makes our triangles a little bit easier to play with. If we were actually doing this with trigonometry, I would make that assumption for a very small observer height, and then I would just use triangle math, trig or geometry, as you wish. However, that's not actually the path I'm going to take with this observation. I'm going to look at it just a little bit differently. Like I said, I want to avoid math. For a start, let's take a look at an observer at point A here. We've got a tower and a mountain. And when the observer is close to the tower, his line of sight through the top of the tower is way up above the mountain, and the mountain appears well below the top of the tower. As that observer moves further away from the tower to point B, then the mountain starts to appear to rise above, let's get the line here, that line there, almost above the top of the tower. When the observer moves to point C, the mountain does indeed appear above the top of the tower. So we're looking at a flat ground plane here. So on a flat ground plane, with these three objects, the observer, the smaller object, and the larger object, though more distant, will eventually, inevitably, always appear above the lower object in front as the observer moves away. Now, that's that can be proven mathematically, and I think Gary has already seen that math and acknowledges it. You get into an issue when the observer is so far away that both the objects are really, really small and hard to see either of them. But if you got your telescope out, you'd be able to see that the top of the mountain would appear above the tower. That is not the case on a curved surface. It depends. So here's a situation on a curved surface. We've got everything lined up. I've got my observer A lined up with the observer A above. He's looking at line of sight through the top of the tower, well above the mountain. He moves further back. Now he's at point B, line of sight, still above but getting closer. He moves further back and he's at C. Line of sight is now with the mountain and the top of the tower lining up. If you were to continue a little bit further, the mountain would begin to appear above the top of the tower. So in this particular arrangement of the three objects, we get the same kind of result as we had on a flat surface. Not identical, but similar. And but it depends on the relative heights and the relative distances. Change those ratios and you start to get a different result. So here I tried to draw things out to scale, and I think this is a nice demonstration of why doing graphical analysis to scale is sometimes problematic. This line represents, to scale, the observer at the left end and the mountain Dow Crag at the right end, and here, that little notch is Blackpool Tower. Now I've drawn Blackpool Tower from the top of the tower to mean sea level at below the top of the tower to scale, and I've done the same for the mountain. The top of the mountain, mean sea level below the top of the mountain to scale. You can get an idea what that means. There's Blackpool Tower. And there's Dow Crag, a quite tall mountain. The little red notch you see here is based on Walter Bisland's curve calculator, the amount of drop that the Earth would have for that distance from our observer. Now the black line, this black horizontal line, represents a flat ground surface. The red indicates how much drop there would be if the Earth is curved. So we're going to look at the next scale diagram here. That would be this one. That's our flat line, and the dashed is our curved line. That's our Earth curved line. And you can zoom in onto the mountain here, and now the red here indicates the mountain with the drop. Okay, so the point of this is that you can see from this diagram that it's really hard to draw this stuff to scale and get helpful information out of it. So I decided not to follow that path, and I decided to do just a variety of scenarios looking at three generic objects: a tall object, a medium-sized object, and an observer at ground surface. So here's a quarter of a circle. It represents a quarter of our globe, and we've got, let's see if I can get it. This here is our ground surface, that curved black dashed line. I've drawn a tall object, I've drawn a shorter object, and then what I did was I started putting in an observer who is at different locations. Here's the observer at the point closest to the tower. We'll call this the tower. He's looking, his line of sight through the top of the tower is above the top of the mountain. So the mountain appears a little below the tower. This is rather similar to the Blackpool photo. As he moves further back, now we look at this green line. He's moved from here further back. His line of sight through the top of the tower reaches a point where it lines up with the mountain. So the mountain and the top of the tower now meet. I'm going to turn off the orange line, and there's the green line. Now he's going to go back further. Now we're looking at this blue line here. So he's moved back from here to there, and his line of sight through the top of the tower puts the top of the tower below the top of the mountain. So for these ratios of heights and distances, the mountain will indeed rise above. And this continues as he moves further back. This diagram is the same as the previous one, but I've added this dashed orange line here. This is a tangent line from the observer's location. So that means that everything between that dashed orange line and the ground surface is hidden below the horizon. So he sees the top of the mountain below the top of the tower. He sees this much of the mountain, and then this part of the mountain is hidden. Now he moves further back. We're looking at the green line, same green line that we saw before, but I've added the green dashed line. Okay, so the green dashed line shows us that a little bit more of the mountain has dropped below the horizon. The top of the mountain's rising to match the top of the tower, but we're also losing a little bit more of the base of the mountain. As he moves back further, turn off the orange, turn on the blue. Now he's moved back from this point to this point, and he can now see some of the mountain. Let me turn off the green. He can now see some of the mountain above the top of the tower. However, again, as in the previous situation, another bit of the mountain's base is hidden from view by the horizon. We see the blue dashed line and the green dashed line. So as he moves further and further away from the tower, he does indeed see the mountain rising up behind the he does indeed see the mountain rising up behind the tower, but he's also losing more and more of the base. Now in the next image, what I'm going to do is I'm going to keep the observers at the same location. I'm going to keep the tower the same, but I'm going to reduce the size of the mountain. So now the mountain is smaller. Still bigger than the tower, but smaller than it was before. Here's our observer at the orange location. He looks through the top of the tower and he sees well above the top of the mountain, but he does indeed see a bit of the mountain, with a large part of the mountain being hidden below the horizon. As he moves back, the top of the tower is still above the top of the mountain, but it's not as much above the top of the mountain, so the mountain appears to be rising behind the tower. It just hasn't overwhelmed the tower yet. And more of the base of the mountain, this part right here, is hidden from view below the horizon. Now he moves back further still. His changed position to where the blue line is. And again, the top of the tower, his line of sight through the top of the tower is above the mountain. And this is the important part, the entire mountain is now hidden below the horizon. We see the blue tangent line from his observation point. So the dashed blue line represents the parts that are hidden. So this is where we come to the it depends part. So in this situation, compared to the previous, although for a while there the mountain was gradually rising up behind the tower, it never got to the top of the tower, and eventually it got hidden below the horizon before it had a chance to overwhelm the tower. So there you go, there's two different situations, and it depends on the ratio of the heights of the objects and the distances between them. We've got a little more to look at here. So now I've got the tall mountain again, and I've pushed my tower further away. Let's see, I had it here, and now I've pushed it further away. Here's our line of sight. The distance from the observer to the tower is the same as I used in the previous diagrams. We see the dashed line representing the amount that's hidden below the horizon of the part of the mountain hidden by the horizon. We see this solid line passing through the top of the tower, and it's above the mountain. The observer moves further back, and I pushed in at this point. The green line is the tangent, so the top of the mountain is just dipped below the horizon here, but we still see the tower. However, it's worth noting that we see only a little bit of the tower because this much of the tower is hidden now by horizon. So the ratios of the distances and the ratios of the heights work together to cause different scenarios, different solutions to the question you posed, Gary. Last diagram. We have a row of towers that are all the same height. This would be something like Lake Pontchartrain. And then for good measure, I've put a small, a medium-sized object and a tall object in the background beyond that row of towers. Now let's look at what our observer is going to see. We've got our observer at the orange location. The dashed line is his the part that's hidden from view. It's the tangent to his location at the surface, and so a little bit of the first tower is hidden, more of the second, more of the third, more of the fourth, and the fifth tower disappears completely. However, he can see the top of the medium height object, and he can see a significant amount of the tall object. In fact, a bit of the tall object actually appears above the top of that first tower. So even though these objects are farther away, because they're taller than these towers here, he does see them even though he can't see a bunch of these towers. Now he's going to move further back. He has moved from the orange location to the green location. And we've got the same green dashed line, which represents the tangent to his location on the sphere. The green dashed line means everything between it and the ground surface, let me turn off the orange, is hidden. So about half of that first tower is now hidden, and 3/4 of the second tower, and the third tower looks like it's just about completely hidden. The fourth and the fifth are all, of course, also hidden. And the medium height object is now hidden below the horizon, whereas the distant object can still be seen and the top of it is rising above the top of the first tower. So in this diagram, I kind of combined both the scenarios by putting in two tall objects, one of them taller than the other, and we see that one of them rises above the front tower, but the other one does not rise above the front tower. It doesn't have a chance to before disappearing below the horizon. So there you go. These are a bunch of different scenarios. They demonstrate how the ratios of the heights and the ratios of the distances all interact. So Gary, you had a photograph of your, taken in Central Valley, of a tree looking, and I believe you were looking towards the coastal range. I think you were looking west in that photograph, and you had the tree, and then beyond the tree, the coastal hills. And those hills were below the tree line. However, you had said that if you were to move back away, at a certain point, those hills would be seen above the tree line. That's very possibly true for that particular set of objects. However, you could find other combinations. A taller tree, for example, or a lower section of the coastal range, or a larger distance between them, where that would not be the case, where although the tree might appear higher than the mountains from one distance, as you move further away, the mountains would gradually disappear behind the tree without ever rising above it. These diagrams show how that would work. I encourage you to go out there, and when you're out there in the fields working in Central Valley, look around for those various situations and see if you can recreate both of those scenarios. I don't know where you are in Central Valley, but there are some parts of the valley where if you look northward, you can see Mount Shasta. It's been a long time since I've been in that part of the country. I left about 10 years ago. But I remember going up Highway 5, and there are points where you can see Mount Shasta from quite a long ways away. So that might provide you with some interesting opportunities for doing some of these long-distance observations. Anyway, this video is getting close to 20 minutes, so I better cut it short here, as there's a lot of material. I didn't intend it to be this long. I hope it's helpful. If it's really necessary to do a repeat of this whole thing with refraction, I will do so, but I'm hoping that this will at least get the point across about how the geometry works. Thanks. Hope this was useful to you all, and have a great day. Bye-bye.